Okay, so last lesson we went through the majority of 22.1, but the one thing that we didn't go through was point 5, which is to understand that a photon has momentum, and that momentum is given by momentum. Remember, we use P for momentum is E over C. Now this is relatively new for CIE. We're not quite sure exactly yet how they're going to examine this. So I'm going to give you quite a lot of detail here, and hopefully that will be it will definitely be enough to get you through your exam, and hopefully it will be some interesting kind of extra hinterland stuff as well. So photons having momentum, it's a strange thing to consider because, as you know, we know that light has no mass. And there's lots of very good physics to prove that light has to not have mass. And yet we can also prove quite easily that light definitely does have momentum. And when you get to university and you study kind of more of it, it starts to make a little bit more sense why that is logically consistent. But here's some good proof for it. So this is often cited as sort of the first really good proof of it, is the Halley-Bopp comet. And actually all comets do this. If you look at the path of a comet, what you see is they actually have two tails. And they have one tail that is dust particles that are kind of left in their wake, but they also always have a tail that points in a straight line away from the sun. So you can see how this, even though at this point the movement of the comet is that way, and there'll be a little tail of dust there, actually the far bigger tail points away from the sun. Now, that doesn't classically make sense unless we consider, well, what must be going on here? Well, what must be happening is we've got photons from the sun coming out, and they're travelling in that direction, and as they hit the dust particles on here, there must be some kind of interaction which is imparting momentum onto these dust particles and making them move away. So that was kind of the first bit of evidence for it. The second piece of evidence came from the concept of Compton scattering. Now, I'm not going to pretend to be an expert at this. I did do X-ray crystallography a lot at university. I never really enjoyed it. So I'm going to go through a really, really simple explanation. If you're not doing CIE A-level physics, you're probably going to want a better source in this, but this is going to be good enough for A-level. So Compton scattering. It was a scientist called Compton, and he was studying the behaviour of X-rays as they hit different types of crystals. And one of the things that he could observe was, he looked at the light hitting a crystal, and particularly how light was interacting with electrons. So what he looked at was photon scattering, or light scattering. Now, scattering is when light hits an object and then reflects or scatters or bounces, or any other kind of woolly term you want to use. Basically, light hits it and leaves again. So what we saw was, we've got E as HF, that gives us the energy of a photon. So a photon has a particular wavelength as it comes in and it hits an electron. Now, the interesting thing was that he was watching these electrons, and they could see that the electrons, they had a change in kinetic energy, and they gained kinetic energy through this interaction. Now, if you think about this, if it's changed its kinetic energy, well, that means its velocity has to have changed. Now, if its velocity is changing, that means that its momentum must have changed as well. So basically, in this interaction, somehow the momentum of these electrons is going up. But we know, and it's a fundamental law of physics, that momentum is always conserved. So what he saw was that the photon had to have changed its momentum as well. The momentum of the photon required to be reduced. And that's actually what he saw. What he saw was that the wavelength increased of these photons afterwards. And again, that kind of makes sense if you think about it. You can think, well, I've imparted kinetic energy here, so the energy of the photon, well, that has to have reduced. If I've had an energy transfer of some energy going into this electron, well, okay, therefore the energy of the photon had to have changed. That's why we kind of put E prime here. This is a reduced energy. And okay, it still makes sense from what we learned last lesson. I can see that because the energy of this photon must have reduced, therefore its wavelength has increased, its frequency has decreased. But, and this is the key bit, well, I've also said that, well, that energy has taken the form of kinetic energy. And if that energy has taken the form of kinetic energy, well, therefore, there must be an increase in momentum here. So over here, the momentum must have decreased because it's a conserved quantity. And well, you have to have momentum in order for momentum to decrease. So that was proof that the electrons did in fact have momentum despite having no mass. And what you can do is if you do a little bit more maths than we'd really be comfortable with at A level, you can prove that momentum is equal to h over lambda, Planck's constant over the wavelength. Now, as you know, h is an absolutely tiny number, so even though wavelength is also small, and so that normally dividing by a very small number makes you a bigger number, well, h is so tiny that the momentum is barely noticeable. We don't really see it in day-to-day life, except when we're dealing with things that are super light, like individual electrons. CIE in their specification, they say that they want us to use momentum as E over C, which just falls out of this equation. You can see that we know that E is hc over lambda, so I could rearrange that to say E over C is equal to h over lambda, and Compton already found that h over lambda is momentum, so E over C therefore is momentum. So momentum shouldn't be a rho, that should be a proper P. So P is E over C, and that's what CIE want you to use. So what will be the applications of this? The kind of thing you might see in a question, and we will do some practice of these in class, but there's a pretty well designed idea of a solar sail now. So the idea of a solar sail is you have your spacecraft, your satellite, or whatever you want, and if you want to sail away from the sun, well, what you do is you have a giant surface here. So what's going to happen is you're going to have all these individual photons coming along and being absorbed by this solar sail and scattered backwards. And as they're scattered backwards, they'll be scattered backwards with a slightly longer wavelength, because what they'll have done is they'll have imparted some energy to this sail, which means that it's going to be increasing the momentum of this sail. And there's actually some pretty cool and interesting work that shows that if you have a spacecraft that you'll want to travel for sort of tens to hundreds of years, you can actually get to far greater velocities using a solar sail method than conventional rocket engines, because although the individual momenta of these photons from the sun are absolutely teeny, if they go on for years and years and years and years and years, well, you have years and years and years of constant increases in momentum, and that can be enough to actually get you up to some pretty large velocities. And when we look at kind of interstellar traveling between stars, some of the best kind of theories of how we could do it actually involve these solar sails, which seems super counterintuitive, but there we go. That is the physics. So, as I say, the syllabus just says understand that a photon's momentum is given by momentum is E over C. The kind of questions we might expect to see might be things like, here's the mass of an object. If you want to accelerate it up to a certain velocity with photons of a certain wavelength, calculate the number of photons or length of time. So we'll practice some of those questions. But actually, as you can see, the maths is relatively straightforward. The concept is a bit weird, but if you can just be confident with the idea that they do have momentum except for mass, their momentum is given by this equation here, then hopefully anything they ask should actually be relatively straightforward.